Can your brain truly grasp infinity? Tonight, we're going to explore the largest galaxy ever discovered and why it breaks our ability to understand scale itself. You've probably heard astronomers talk about big numbers in space before. Billions of stars, trillions of planets, distances measured in light years. But here's what most people don't realize. There's a galaxy out there so impossibly massive that it challenges our fundamental capacity to comprehend size. By the end of this journey, you're going to understand exactly why the human brain hits a wall when confronted with true cosmic scale, and why this one galaxy represents the absolute limit of what we can mentally process. Before we dive in, if you enjoy these kinds of explorations, a quick like or a subscribe really helps the channel grow. It's a small thing for you, but it makes a real difference for me. Get comfortable. Let's begin. There exists in the universe a structure so gigantic that it defies all human capacity for proportional and visual comprehension. Alcyoneus is a galaxy situated 3 billion light-years from Earth in the constellation Lynx. Its plasma jets extend for 16 million light-years from one end to the other. To put this in context in a way you can begin to process, a light-year is the distance that light travels in an entire year, about 9.46 trillion kilometers. If we wanted to draw Alcyoneus on the same scale as Earth, our planet would simply disappear before it could even become a visible dot. The proportions are so extreme that any attempt at visualization breaks down before it begins. Here's the fundamental issue we need to face together. It's not a question of having better telescopes or sharper images. The problem lies in the very architecture of the human brain. Our perception evolved to deal with distances between trees, mountains, at most the terrestrial horizon in the distance. We developed the ability to judge whether a saber-toothed tiger was 50 meters away or 100 meters away because that difference meant life or death. But trying to visualize 16 million light-years is like asking an ant to comprehend the curvature of the entire Earth. We begin this journey where everyone begins, with the familiar, the tangible, what we can touch and measure. The Earth seems immense when we walk across it. 75 kilometers of circumference around the terrestrial equator. If a person walked without stopping, it would take about a complete year to circle the planet. That's already a distance that challenges our direct experience. How many of us have walked for a full year? The Moon orbits at 384,400 kilometers distance, approximately 30 Earth diameters, separating the two celestial bodies. When you look up at the Moon tonight, you're seeing something nearly 400,000 kilometers away. Light from the Moon takes 1.3 seconds to reach your eyes. That's farther than any human has traveled, except for the 24 Apollo astronauts who made the journey between 1968 and 1972. The Voyager 1 probe, launched in 1977, is the most distant human object. It has already traveled 24 billion kilometers over nearly 5 decades of flight. Even so, Voyager 1 still hasn't completely left the gravitational influence of our Sun after 47 years of traveling, at speeds no human has ever achieved. It's moving at about 17 kilometers per second, fast enough to circle the Earth in 40 minutes, yet it's still essentially in our cosmic backyard. These distances already begin to stretch our intuition. Few can mentally visualize 24 billion real kilometers. Your mind starts to treat these numbers as abstractions rather than actual distances. And we haven't even begun to approach the scale of Alcyoneus. If Earth were a basketball 24 centimeters across, the Moon would be a tennis ball orbiting 7 meters away. Mars would be 59 meters from that basketball Earth, already beyond clear visual range on a cloudy day. Jupiter would sit at 640 meters, farther than 6 football fields placed in sequence, one after another. Neptune would be at an incredible 3.7 kilometers distance, already outside direct visual range without equipment assistance. And this is just our tiny solar system. The solar system, this minuscule realm compared to the cosmos, already completely transcends our intuitive capacity for spatial visualization. In our basketball Earth scale, the nearest star beyond the Sun, Proxima Centauri, would be 160,000 kilometers away. That's nearly half the real distance from Earth to the Moon. So even in a scale where Earth fits in your hands, the nearest star would require a journey across continents. And we haven't even left our cosmic neighborhood yet. Alcyonius was discovered in 2022 by Martin Oey and colleagues using LOFAR, the European Radio Telescope Network. LOFAR consists of approximately 20,000 radio antennas distributed across 52 locations throughout Europe. It's a technological marvel in itself, a distributed telescope with eyes spanning an entire continent. The discovery happened when reprocessing old data with a new technique, removing compact sources that interfered with previous detections. Sometimes the most profound discoveries come not from looking at new data, but from seeing old data with fresh eyes. The astronomers found by chance a structure so faint and diffuse that earlier telescopes simply couldn't detect it, like finding the outline of a ghost in static. When Oey saw the lobes of Alcyonius in the images, he didn't immediately realize he had made a historic discovery. The radio emissions were so faint, so spread out, that they appeared as barely perceptible wisps against the cosmic background. Only when he measured the full extent did the magnitude become clear. This wasn't just another radio galaxy. This was something unprecedented in its sheer scale. The host galaxy itself is surprisingly ordinary, stellar mass of 240 billion solar masses, black hole of 400 million solar masses. Nothing exceptional by galactic standards. If you encountered this galaxy without knowing about its jets, you'd classify it as thoroughly average, unremarkable in every way, except for the colossal structure it has created. But here is where the story becomes extraordinary. From this ordinary galaxy extends something extraordinary. Jets of plasma traveling at nearly the speed of light, carrying magnetic fields and charged particles across distances that dwarf entire galactic clusters. The jets have been active for approximately 50 million years, creating these structures grain by grain, particle by particle, across cosmic time. In September 2024, Porphyrion dethroned Alcyonius. Its jets extend for an impressive 23 million light-years across the cosmos. Porphyrion is 7.5 billion light-years distant, existing when the universe had only 6.3 billion years of age. We're seeing it as it was when the universe was less than half its current age. The light we observe began its journey before Earth had developed complex multicellular life. In December 2024, TXS Sotplatu 52 surpassed Porphyrion with an estimated 26 million light-years of total extension between ends. Each discovery pushes the boundary further, revealing that our previous understanding of maximum galactic scales was laughably inadequate. More than 10,000 giant radio galaxies have been discovered in the LOFAR survey. Far more than the hundreds known previously. What we thought were rare cosmic oddities turn out to be common features of the universe. These galaxies aren't rare anomalies. They may have influenced galaxy formation in the primitive universe much more than we ever imagined. They're rewriting the textbooks as we speak. The discovery of such colossal structures reveals that our understanding of the cosmos was severely underestimated and limited until recently. We thought we knew the scale of things. We mapped galaxies, measured their sizes, calculated their masses, but we missed these titans hiding in plain sight, invisible to our earlier instruments. We were looking at the universe through a keyhole and thinking we saw the whole room. Alcyonius received its name in honor of the giant from Greek mythology, son of Uranus, primordial god of the sky. In mythology, Alcyoneus was one of the giants who fought against Hercules, immortalizing himself as a symbol of tremendous strength. The name is appropriate. Just as the mythological giant challenged gods, this galaxy challenges our very cosmic understanding. It forces us to confront the inadequacy of our mental models. But before we dive into the incomprehensible depths of Alcyoneus, we need to build a ladder of gradual, progressive understanding. Each rung of this ladder amplifies our perspective 10, 100,000 times until numbers lose tangible meaning. We're preparing now to climb from the familiar to the incomprehensible, from the terrestrial to the truly cosmic and absolutely transcendental. This journey isn't just about distances. It's about the limits of human cognition when faced with the revealed infinite. Your brain evolved to navigate African savannas, to judge the distance between predators and prey, to estimate whether you can leap across a stream. That same brain is now being asked to process structures that span significant fractions of the observable universe itself. Think about that for a moment. The very organ you're using to understand these words, the neural networks firing as you read, evolved for survival in an environment where the longest meaningful distance was perhaps to the horizon, maybe 5 kilometers on a clear day from a hilltop. Your ancestors needed to distinguish between a mammoth 100 meters away and one 200 meters away. They never needed to contemplate 16 million light years. And now we're asking that same brain to comprehend something 16 million light years across? It's not your fault that this feels impossible. It's not a personal failing. It's a fundamental limitation built into the architecture of human consciousness. We can calculate these distances, we can measure them, we can work with them mathematically, but we cannot truly visualize them, cannot hold them in our mind's eye, the way we can picture our childhood bedroom or the route to work. Evolution shaped us to understand the scale of survival, not the scale of the cosmos. Our brains simply weren't designed for this. And yet, we've found ways to transcend these limitations. Through mathematics, through technology, through the patient accumulation of human knowledge across generations, we've reached out across 3 billion light-years of space and time to detect this cosmic giant. We've found something so large that 160 of our entire galaxies could be lined up end to end within its structure, something that challenges every assumption we had about the maximum size of cosmic objects, something that exists on a scale that breaks our capacity for intuitive understanding. We begin with the Sun, our nearest star, the gravitational center of everything we know as our planetary home. The Sun sits 149.6 million kilometers from Earth, a distance we call 1 astronomical unit, or AU. Sunlight takes exactly 8 minutes and 20 seconds to travel this distance and warm our faces each day. Think about that for a moment. When you feel the sun's warmth on your skin, you're experiencing light that began its journey over 8 minutes ago. You're touching the past. If the sun were the size of a basketball, Earth would be a peppercorn orbiting 26 meters away. At this scale, Jupiter would be a small orange at 134 meters, while Neptune would sit at an impressive 800 meters from our basketball sun. The Voyager 1 probe, humanity's most distant object, would be only 2.6 kilometers away in this proportionally diminished solar system. But even these analogies begin to strain under the weight of reality. The Sun contains 99.86% of all mass in the solar system. The planets, including our Earth, are gravitational crumbs orbiting a thermonuclear giant. Its mass is approximately 1.989 times 10 to the 30th power kilograms, about 333,000 times Earth's mass. Numbers that slide off the mind like water off glass. At the solar core, 600 million tons of hydrogen fuse into helium every single second, releasing energy equivalent to 100 billion hydrogen bombs per second. This nuclear furnace has burned steadily for 4. 6 billion years and will continue for another 5 billion before expanding into a red giant, long after human civilization has either transcended its origins or vanished entirely. But here's what should humble us. The Sun is merely an average star. There exist stars 100 times more massive and 10,000 times more luminous. Our life-giving star around which our entire existence revolves is cosmic middle management. The nearest star beyond the Sun is Proxima Centauri, located 24 light-years away, or 40 trillion kilometers from here. Even traveling at Voyager 1's impressive speed of 61,000 kilometers per hour, it would take 73,000 years to reach Proxima Centauri in a straight line. That's longer than all of recorded human history. In our basketball sun scale, Proxima Centauri would be an incredible 6,800 kilometers away, approximately the distance between Lisbon and New York. So even when we shrink our entire solar system to fit in a large room, the nearest star requires intercontinental travel to reach. Here begin the first cracks in our spatial intuition. Distances between stars are abysses of almost absolute void. Interstellar space isn't completely empty, but it might as well be. It contains about 1 hydrogen atom per cubic centimeter, a density so absurdly low that the best laboratory vacuum on Earth seems crowded by comparison. If you could gather all the empty space of the Milky Way and compress it, you'd have only a few million stars worth of solid matter. The universe is mostly nothing, punctuated by occasional islands of something. Sirius, the brightest star in our night sky, sits 8.6 light-years away, twice as distant as Proxima Centauri. When you see Sirius twinkling tonight, you're seeing light that began its journey when someone 8.5 years younger was looking up at that same sky. Betelgeuse, the red supergiant in Orion's shoulder, resides approximately 550 light-years away, already completely beyond any intuitive proportional visualization. If Betelgeuse exploded today as a supernova, we would see the spectacle only 550 years from now in the full 26th century. Children born today would never see it, nor would their children nor their children's children for dozens of generations. The light we see from Betelgeuse right now departed from it when the great navigations were beginning on Renaissance Earth. Columbus was discovering the Americas, while this light started its journey across the cosmic void to reach your eyes tonight. You are seeing the medieval past of a star. Our galaxy, the Milky Way, contains between 200 and 400 billion stars scattered across a flattened spiral structure. If we counted 1 star per second without stopping, it would take between 6,300 and 12,600 years just to count all the stars in our galaxy, longer than all of human civilization. The Milky Way spans about 100,000 light-years in diameter across its main stellar disk, where most stars reside, but if we include the invisible dark matter halo, its true diameter extends to almost 1.9 million light-years through the void. We live inside something so vast that light takes 100,000 years to cross it. The Sun orbits the galactic center at 230 kilometers per second, completing 1 full orbit every 230 million years. The last time our solar system was in this orbital position, dinosaurs had not yet appeared on the primitive Earth. Our planet has traveled once around the galaxy since the Permian extinction, when 90% of all species died. At the center of the Milky Way resides Sagittarius A, a supermassive black hole with 4.3 million solar masses compressed into a minuscule volume. This black hole has a diameter of approximately 23.5 million kilometers, about 60 times the Earth-Moon distance, gravitationally flattened, an object so dense that if you could somehow approach it, time itself would slow to a crawl. We live 26,000 light-years from the galactic center, residing in the Orion Arm, a quiet suburb of our larger spiral galaxy. If the Milky Way were a football field, our solar system would be a grain of sand near the 50-yard line. Not special, not central, not particularly noteworthy in any cosmic sense. Our galaxy rotates like a flattened disk similar to pizza dough when a chef spins it rapidly in the air. The thickness of the Milky Way is only 1,000 light-years at the edges, making it appear extremely flattened when viewed from the side. Like a cosmic pancake scattered with hundreds of billions of glowing points, we can already perceive that our location is modest, neither near the center nor at the edge, just floating in the galactic middle ground. Cosmic suburbanites in an average neighborhood of an average galaxy. But the Milky Way isn't alone. It belongs to the local group, a collection of about 54 galaxies gravitationally bound together. Andromeda, our larger galactic neighbor, sits 5 million light-years away and approaches us at 110 kilometers per second. In approximately 4.5 billion years, Andromeda and the Milky Way will collide, merging into a single giant elliptical galaxy dubbed Milkomeda. Despite the name collision, individual stars will rarely actually collide. The space between them is too vast for direct massive impacts. It will be more like two swarms of fireflies slowly interpenetrating. Observing the Milky Way from Earth means seeing only a slice of it. We live inside the disk, unable to see it complete. It's like trying to understand the shape of a forest when you're lost in the middle of the dense trees around you. We can map it, measure it, model it, but we can never step outside to see it whole. This limitation extends beyond mere perspective. It represents something fundamental about the human condition. We are always inside what we're trying to understand. Embedded observers, attempting to comprehend the system we're embedded within, whether it's our galaxy, our universe, or our own consciousness. The Milky Way contains stellar nurseries where new stars are born from collapsing clouds of gas and dust, stellar graveyards where ancient stars have exploded or faded away, planetary systems around nearly every star, many potentially harboring worlds where liquid water could exist. In our galaxy alone, there may be billions of planets capable of supporting life as we know it. Yet for all this abundance, for all these hundreds of billions of stars and potentially trillions of planets, we have found no confirmed signs of other intelligent life. The galaxy that seems so crowded with possibilities appears eerily quiet when we listen for artificial signals. Either intelligence is far rarer than we hope or far more common than we can detect. Some scientists estimate that there should be millions of technological civilizations in our galaxy right now. Others argue that we might be among the first or among the last, or entirely alone. The Fermi paradox asks, where is everybody? If the galaxy is so vast and so old, why haven't we encountered anyone else? Perhaps the answer lies in scale itself. Perhaps civilizations arise and fall in cosmic moments. Perhaps they transcend physical existence. Perhaps they're all around us but operating on scales of time and space we can't perceive. Perhaps the vast distances between stars form an impenetrable moat around each world, keeping intelligence isolated despite its abundance. The light from distant stars in our galaxy has been traveling for thousands or tens of thousands of years to reach us. When we look at the night sky, we see the ancient past of our galactic neighborhood. Some of those stars may have already died, their light still traveling toward us like messages from the dead. And yet, even the immensity of the Milky Way is merely the beginning. The journey to Alcyonius has barely begun in earnest. Beyond the local group exist thousands of galactic clusters, each containing hundreds or thousands of individual galaxies bound together by gravity's invisible hand. The Virgo cluster, our largest neighbor, contains about 1,300 galaxies scattered across a volume of 15 million light-years. Think about that scale for a moment. 15 million light-years just for one cluster. A distance so vast that light itself, traveling at its ultimate cosmic speed limit, takes 15 million years to cross from one side to the other. Virgo sits approximately 53 million light-years away. The light we see from it departed when the first ancestors of modern horses were appearing on Earth. Those early proto-horses, no larger than dogs, were grazing in ancient forests, while photons began their journey across the cosmic void to reach our telescopes today. The light arriving at your eyes tonight carries information from an Earth where no grass yet existed, where flowers had not yet evolved, where the very concept of a mammal larger than a house cat was still millions of years in the future. M87, the giant elliptical galaxy at Virgo's center, contains about 1 trillion stars, 5 times more than our entire Milky Way. If our galaxy is a city, M87 is a continent. A stellar empire so vast that if you could count 1 star per second, it would take you over 30,000 years to count them all. The supermassive black hole at M87 center has 6.5 billion solar masses, 1,000 to 500 times more massive than Sagittarius A. In 2019, the Event Horizon Telescope captured the first image of a black hole, precisely this monster at M87 center. That historic image showed an orange ring of light surrounding a dark shadow. The event horizon, the gravitational point of no return, beyond that boundary, not even light can escape. Space and time themselves become so warped that our physics breaks down into mathematical poetry. The ring of light we see isn't the black hole itself. It's matter spiraling to its doom, heated to billions of degrees by gravitational compression. Matter moving so fast and under such extreme conditions that it glows brighter than the cores of stars. And yet this blazing funeral pyre of doomed matter orbits something so dark it makes the space between galaxies seem brilliantly illuminated. M87 expels a jet of plasma from its black hole, extending 5,000 light-years through surrounding intergalactic space. But even this impressive structure pales compared to what we're building toward. M87's jet is merely a warm-up act for the cosmic giants we're about to encounter. It's like comparing a garden hose to the Amazon River. IC 1101, previously considered the largest known galaxy, spans about 6 million light-years in visible stellar diameter. It contains approximately 100 trillion stars. If the Milky Way is a city, IC 1101 is an entire stellar continent located 1 billion light-years from Earth at the center of the Abell 2029 cluster, gravitating massively in deep space. The light we see from IC 1101 today departed when complex multicellular organisms were just beginning to evolve in Earth's primitive oceans. Single-celled life was discovering cooperation, learning to work together in ways that would eventually lead to consciousness, to intelligence, to the very minds now contemplating IC 1101's ancient light. When those photons began their journey, the most complex life on Earth was pond scum. And yet, they carried within their electromagnetic patterns the image of a galaxy containing more stars than there are grains of sand on all Earth's beaches. But even IC 1101, with its impressive vastness, has been surpassed by the discovery of radio galaxies with even larger structures. This is where our journey takes a dramatic turn, where we encounter objects that challenge every assumption about maximum cosmic scales. Where the universe reveals that our most generous estimates of big were still embarrassingly modest. Radio galaxies are galaxies with active supermassive black holes that eject plasma in giant bipolar jets. These jets travel at velocities approaching light speed, carrying charged particles and intense magnetic fields through empty space. When the jets decelerate after traveling millions of light years, they form gigantic lobes that shine brilliantly in detectable radio waves. Hercules A, a visible radio galaxy, possesses jets extending 1.5 million light-years, 15 times the diameter of the Milky Way. Compared to Hercules A's stellar disk, The jets are 10,000 times larger, a proportion that is absolutely surreal and forever disconcerting. The galaxy itself, with its hundreds of billions of stars, becomes almost a footnote to its own creation. Imagine an ant carrying a spider web the size of an entire football stadium. That's the approximate visual proportion we're dealing with. Something so small creating something so impossibly vast that analogies begin to collapse under their own inadequacy. It's like finding that a grain of rice has somehow constructed the Golden Gate Bridge. Centaurus A, the nearest active galaxy to Earth, has jets extending about 1 million light-years. Its jets are visible across multiple wavelengths, radio, infrared, X-rays, forming a complete cosmic multispectral spectacle. The total energy released by Centaurus A's jets equals the energy output of trillions of stars like our Sun, and this energy flows continuously, year after year, for millions of years. How can black holes which emit no light create jets so bright and energetic as they traverse the dark intergalactic cosmos? The answer lies in one of the universe's most elegant mechanisms. As matter spirals toward the black hole, it forms an accretion disk, a structure of superheated orbiting gas that glows brilliantly. The accretion disk is like a cosmic whirlpool of matter. As particles approach the center, they spin faster and grow hotter, reaching temperatures of millions of degrees, hot enough to strip electrons from atoms, creating a plasma so energetic it outshines entire stellar neighborhoods. Magnetic field lines in the disk twist and coil like invisible DNA helixes, channeling charged particles into narrow beams at the magnetic poles. These beams are the jets, streams of magnetized plasma accelerated to 99.9% of light speed by the continuously released gravitational energy. The power of the jets depends on how fast the black hole feeds. The more matter it devours, the more powerful the jets become exponentially. It's a cosmic engine with no moving parts, powered by the fundamental architecture of spacetime itself. This is where Alcyoneus enters our story in earnest. Alcyoneus has a relatively modest black hole, but its jets extend 16 million light-years, 160 Milky Ways aligned consecutively. Porphyrion surpasses even this with 23 million light-years. 140 galaxies the size of our Milky Way lined up end to end. These numbers begin to lose meaning, begin to slide off consciousness like water off glass. But let's try to anchor them. If you could drive a car at highway speeds across Alcyoneus, the journey would take 170 trillion years, longer than the universe has existed by a factor of 12,000. If you walked across it at normal walking pace, you'd need longer than stars will continue to shine in the universe. These jets don't merely traverse the void. They inject energy, magnetism, and particles into the surrounding diffuse intergalactic medium. They may have played a crucial role in galaxy formation in the primitive universe, when densities were much higher than we currently observe. They're cosmic gardeners, seeding space with the elements and energy needed for new structures to grow. The discovery of thousands of these giant radio galaxies rewrites our understanding of how cosmic structures evolve through time. They're not rare anomalies, they're fundamental components of the cosmic ecosystem, influencing scales that completely transcend individual galaxies. What we thought were isolated island universes turn out to be connected by invisible bridges of energy and magnetism. But here's the question that should make you pause. How can something originating from a single galaxy extend across distances comparable to the structures of the observable universe itself? To answer this, we need to understand the cosmic web, the fundamental architecture that organizes all matter in the known universe. Galaxies don't distribute randomly through space. They form filaments, walls, clusters, separated by enormous voids, almost devoid of visible or measurable matter. This structure emerged from tiny density fluctuations in the primordial universe, amplified by gravity over billions of evolutionary years. Picture the universe as a vast, three-dimensional spiderweb. Galaxies cluster along the strands. Vast, empty spaces lie between them. The strands themselves can stretch for hundreds of millions of light years, connecting superclusters of galaxies in a network that spans the observable cosmos. If you could shrink the universe until the Milky Way was the size of a marble, this cosmic web would still stretch across continents. The cosmic web began forming when the universe was very young, less than 400,000 years old. At that time, tiny quantum fluctuations in the density of matter were stretched by cosmic expansion into the seeds of all future structure. Regions slightly denser than average attracted more matter. Regions slightly less dense became the voids, like ripples in a cosmic pond. These initial disturbances grew and evolved over billions of years. Over billions of years, gravity sculpted these initial irregularities into the magnificent cosmic architecture we observe today. Dark matter, 5 times more abundant than ordinary matter, provided the gravitational scaffolding, but we can only see the ordinary matter that follows dark matter's invisible blueprint. We're seeing the decorations on a building whose structure remains hidden. The jets of Alcyonius and Porphyrion can traverse entire filaments, potentially reaching the voids between structures in the larger cosmic web. Think about what this means. These objects, born from single galaxies, grow large enough to bridge the fundamental organizational structures of the universe itself. They're not just inhabitants of the cosmic web, they're among its architects. When we observe Alcyonius at 3 billion light-years distance, we're seeing it as it existed when the universe was about 3/4 of its current age. When Porphyrion's light began its journey 7.5 billion years ago, the universe was less than half its present age. We're witnessing these giants as they were in cosmic youth, when the universe was more compact, denser, more dynamic. At those earlier epochs, galaxy formation was more vigorous, star birth rates were higher. Black hole feeding was more common. The cosmic web was tighter, with shorter distances between its major nodes. Jets like those of Porphyrion could more easily traverse significant fractions of the universe's organizational structure. These ancient jets may have helped regulate star formation across cosmic time. By heating the intergalactic medium, they could prevent gas from cooling and collapsing to form new galaxies. They may have imposed a cosmic thermostat, controlling the rate at which the universe converted gas into stars. Every galaxy, including our own, may exist in its current form, partly because of the regulatory influence of these distant giants. We're now at the frontier, where individual objects begin to compete in size with the very organizational structures of the universal cosmos. The cosmic web is the large-scale structure of the universe. Filaments of galaxies intertwined like neurons in a gigantic brain. Each filament can extend for hundreds of millions of light years, connecting massive superclusters gravitationally entangled with one another. Picture the most complex neural network you can imagine, then scale it up until each connection spans distances that dwarf entire galactic neighborhoods. Between the filaments reside the cosmic voids, regions with extremely low density, containing few or no visible, observable, detectable galaxies. Typical voids have diameters of 100 to 400 million light-years. If the Milky Way were a grain of sand, these voids would be gigantic empty rooms. Not just empty rooms, but empty cathedrals, empty aircraft hangars, empty spaces so vast that the very concept of room becomes meaningless. The Great Wall of Sloan, discovered in 2003, is one of the largest known structures. 37 billion light-years in total measurable length. If the Milky Way were a grain of rice, the Great Wall would be longer than 10 football fields arranged consecutively in a line. But even this incomprehensible structure pales before what we're building toward. The Laniakea supercluster, our home on the scale of superclusters, has a diameter of 520 million light-years and contains approximately 100,000 galaxies. Laniakea means immeasurable heaven in Hawaiian, an appropriate name for something that completely defies any attempt at direct proportional human visualization. We live inside something called immeasurable heaven, and we're only now beginning to map its boundaries. All this cosmic structure originated from microscopic quantum fluctuations in the primordial universe immediately after the initial explosive Big Bang. These fluctuations, smaller than an atom, were stretched by cosmic inflation to astronomical dimensions in an infinitesimal fraction of a second. Imagine the entire observable universe compressed to the size of a marble, then expanded to its current scale in less time than it takes light to cross a proton. As the universe cooled, gravity amplified these subtle density differences. Regions slightly denser attracted progressively more matter, over 13. 8 billion years, these tiny seeds grew into the galaxies, clusters, and filaments we see distributed everywhere today. Every structure you see in the night sky, every galaxy, every cluster, traces its ancestry back to quantum foam in the first moments after creation. The cosmic web contains about 5% ordinary matter, 27% dark matter, and 68% dark energy. Mysterious invisible components that dominate reality. Think about that. Everything you've ever seen, touched, or experienced represents less than 1/20th of what actually exists. We're like deep-sea creatures who have evolved to see only the faintest bioluminescence, unaware that above us stretches an entire universe of sunlight. Dark matter emits no light whatsoever. We only know it exists because its gravity clearly influences the movement of visible galaxies. Without dark matter, galaxies would spin so fast they would tear themselves apart. It acts like invisible gravitational glue, keeping everything structurally cohesive, 5 times more abundant than all the atoms in the universe, yet completely invisible to every instrument we've ever built. Dark energy is even more mysterious, a repulsive force that accelerates the universe's expansion, making everything move away from everything else increasingly. Discovered in 1998, dark energy surprised astronomers. We expected gravity to decelerate cosmic expansion, but paradoxically it's accelerating. The universe isn't just expanding, it's expanding faster every moment. If dark energy continues dominating, the universe will expand eternally until all distant galaxies disappear beyond our observable horizon. Trillions of years from now, future observers will see only their own local galaxy. The rest of the universe will have become completely invisible and inaccessible. Future civilizations will inhabit island universes isolated in an ocean of expanding darkness. But let's return to the present. Where exactly does Alcyoneus fit into this cosmic web of structures intertwined between filaments and immense voids? Alcyoneus resides in a filament of the cosmic web, not in a dense cluster. Its environment is relatively solitary and sparsely populated. The nearest galactic cluster is 11 million light-years away. Alcyoneus is an isolated galaxy growing in relative solitude. This isolation may explain why its jets grew so large. Without dense obstacles, the plasma could travel freely across unimaginably colossal distances. In denser environments, jets collide with dense intergalactic gas, decelerating and bending like smoke in a constant external wind. But Alcyoneus had space, vast, empty space, stretching in every direction. Its jets could grow unimpeded, like rivers finding the path of least resistance across an endless plain. Porphyrion also resides in a filament. When the universe had half its current age, filaments were closer together, spatially compressed. This means Porphyrion's jets traversed a larger portion of the cosmic web than a comparable jets in today's expanded universe. They were crossing not just empty space, but significant fractions of the universe's fundamental architecture. These ancient jets may have influenced the formation of neighboring galaxies, injecting energy that heats intergalactic gas and prevents gravitational collapse that forms local stars. They may have magnetized the intergalactic medium. Magnetic fields observed in cosmic voids may come from these giant, ancestral, primordial jets. Every patch of seemingly empty space may bear the magnetic fingerprints of long-dead galactic giants. Before LOFAR, we thought jets remained confined to host galaxies or their immediate surroundings. We were completely and absurdly wrong. Now we know that supermassive black holes don't just govern galaxies. Their influence reaches the scale of the cosmic web's universal structural framework itself. They're not just galactic phenomena, they're cosmic architects shaping the largest structures we can observe. Every place in the universe may have been affected by black hole activity at some moment in cosmic temporal evolutionary history. This connects everything. Relatively microscopic black holes connect to the universe's largest structures through their colossal traversing energetic jets. From the smallest scales to the largest, from quantum mechanics to cosmic architecture, everything influences everything else. Our journey began with the Sun, an average star. Now we're discussing objects that extend across significant fractions of the entire observable universe. We've climbed from human scale to stellar scale, to galactic scale, to cosmic scale, and we still haven't answered the central fundamental question: why can't our brain really comprehend these immense proportional cosmic scales? The answer lies in biology. Our brain evolved to survive on the African savanna, not to navigate abstract, distant intergalactic voids. Human depth perception works well up to about 20 meters. Beyond that, we depend on subtle environmental, contextual, comparative clues. We evolved to distinguish between a predator 50 meters away and one 100 meters away because that difference meant survival. We never needed to contemplate cosmic filaments. We have no instinctive references for 16 million light years. It's like asking a mechanical calculator to solve Einstein's general relativity equations. We can calculate, model mathematically, visualize in computer simulations, but we cannot intuit these distances viscerally the way we naturally feel meters. Our neural architecture simply wasn't designed for this scale. Every analogy we create inevitably fails. Football fields, grains of sand, everything collapses under the weight of truly astronomical scale. When we say Alcyonius spans 16 million light years, we're using words that have no experiential meaning. The numbers are real, the distances are real, but our comprehension remains forever abstract. Think about how you perceive your immediate environment. You can sense the distance to your coffee cup, estimate whether you can reach the light switch, judge if you have room to turn around. This intuitive spatial awareness evolved over millions of years of natural selection. Ancestors who misjudged distances fell off cliffs, got caught by predators, failed to reproduce. Good spatial judgment literally shaped our species. But cosmic distances exist in a realm beyond evolution's reach. Natural selection never favored genes that could intuitively grasp the distance to Andromeda. There was no reproductive advantage to understanding galactic clusters. Our ancestors who worried about light years instead of saber-toothed tigers didn't leave many descendants. This creates a profound cognitive limitation. We can work with cosmic scales mathematically, but we cannot feel them. We can manipulate the numbers, but the reality behind the numbers remains forever alien to direct experience. It's not a personal failing, it's a species-wide limitation built into the architecture of consciousness itself. Computer simulations help bridge this gap. We can fly through virtual representations of the cosmic web, zoom from Earth to Alcyonius in seconds. But even these visualizations remain fundamentally abstract. We're watching pixels on screens, not experiencing real cosmic distances. The simulation is not the territory. Professional astronomers work with these scales daily, but even they admit the numbers feel abstract. Martin Oy, discoverer of Alcyonius, said he didn't immediately perceive the magnitude of his discovery. His brain, trained and experienced as it was, still underestimated the scale naturally and intuitively. This limitation extends beyond individual psychology. It shapes how we communicate about the cosmos. Every popular science article struggles with the same challenge. How do you convey unimaginable scales to minds that evolved for the imaginable? How do you translate the cosmic into the comprehensible? We're preparing now for the next step, to see how this cognitive limitation manifests when we attempt to really visualize Alcyonius in its complete proportional magnificence. Let's attempt a thought experiment. Imagine scaling the universe so that Earth fits in the palm of your small hand. In this scale, Earth would have about 5 centimeters in diameter, approximately the size of a small, compact golf ball. You could hold our entire world between your thumb and forefinger, feeling its weight, rolling it around like a marble containing all of human history. The Moon would orbit 1.5 meters away from this golf ball Earth. Already beyond the reach of your completely extended arm, the distance that light covers in 1.3 seconds now requires you to walk across a room. Our celestial companion, which dominates our night sky and pulls our tides, becomes something you'd need to stretch to touch. Even in this compressed universe, the Moon feels distant. The Sun would sit 584 meters away, almost 6 football fields distant, already difficult to visualize simultaneously with the initial golf ball Earth. You'd need to climb to the top of a tall building to see both Earth and Sun in the same field of view. And even then, the Sun would appear as a distant basketball, barely visible on the horizon. The star that gives us life becomes a speck, requiring binoculars to see clearly. Jupiter would float 3 kilometers away, beyond clear visual horizon, already requiring a significant walk to reach it physically. You'd need to leave your neighborhood, cross several city blocks before encountering this scaled-down gas giant. The largest planet in our solar system becomes something requiring a long hike to visit. Neptune would sit at an incredible 17.6 kilometers. You'd need to drive about 15 minutes in a straight line on the highway to reach it spatially. Our outermost planet becomes a destination requiring automobile travel. Proxima Centauri, our nearest star, would be 160,000 kilometers away, almost half the real Earth-Moon distance, crossing entire oceanic continents. Even in our drastically compressed universe, the nearest star requires intercontinental travel. It's farther than the real distance from New York to Sydney, from London to Tokyo. You could circumnavigate the real Earth 4 times before covering the distance to our scaled Proxima Centauri. The center of the Milky Way would sit 1 billion kilometers away, 2.5 times the real Earth-Saturn distance, already in the outer solar system territory. Our galaxy's heart would be more distant than the real orbit of Jupiter, and the complete Milky Way would span 3.9 billion kilometers in diameter, almost the real Earth-Neptune distance, but everything still proportionally compressed and mathematically scaled. Andromeda would be 97.5 billion kilometers away, 650 times the real Earth-Sun distance, penetrating deeply into the distant Oort comet cloud. Our nearest galactic neighbor would require a journey beyond the edge of our actual solar system. Even in this compressed scale where Earth fits in your palm, Andromeda remains astronomically distant. Now comes the moment of truth. Alcyonius, with its 16 million light-years, would measure 623 trillion kilometers in this artificially reduced proportional scale. To put this in context that might help your brain process it, it's 4,160 times the real Earth-Sun distance, or 65 real light-years of travel at continuous light speed without interruption. Even in this drastically reduced scale, Alcyonius remains utterly incomprehensible. Abstract numbers don't translate into direct, visceral, intuitive visual comprehension. Our golf ball Earth becomes meaningless when we try to relate it to something 623 trillion kilometers away. The compression that made Earth holdable in your hand does nothing to make Alcyonius imaginable. Let's try another temporal approach, converting space to time. If each light year were 1 second of elapsed time, how much time would Alcyonius represent completely? 16 million light years would equal 16 million seconds, approximately 185 consecutive days, slightly more than 6 complete terrestrial calendar months. Porphyrion would equal 266 days. Almost 9 complete months of typical, average, normal, biologically natural human gestation. Enough time for a human baby to develop from conception to birth. The Via Lactea at 100,000 light years would equal 100,000 seconds, about 27.8 hours, or slightly more than 1 complete terrestrial rotational day. Proxima Centauri would be only 4.24 seconds away, the time it takes to speak 1 short, complete sentence, normally and articulately, less time than it takes to sneeze. This temporal compression helps somewhat. 6 months is conceivable. We can imagine half a year passing progressively, day after day, slowly. We've experienced pregnancies. We've waded through summers. We understand what 185 days feels like. But this temporal analogy doesn't capture spatial vastness. Time and space are never really equivalent in direct, intuitive, human cognitive perceptual experience. Our brains process temporal duration differently from spatial extension. 6 months feels manageable because we've lived through it, but 16 million light years remains abstract because we never could experience traveling such distances. When we observe Alcyonius through radio telescopes, we don't see a galaxy in any conventional sense. We see 2 faint orange dots separated in digitally processed radio telescope images. Ghostly wisps of electromagnetic radiation that have traveled 3 billion years to reach our instruments. The radio lobes are so diffuse, so sparse in density, that they contain proportionally less matter than the void between them. If you could somehow fly through one of Alcyonius's radio lobes, you probably wouldn't notice anything unusual. The density would be only slightly superior to the common normal surrounding intergalactic vacuum. You'd be traveling through something technically denser than empty space, but practically indistinguishable from nothingness. It would be like swimming through the thinnest possible mist. The host galaxy at the center, with its 240 billion stars blazing like cosmic furnaces, would appear as a tiny bright point between the gigantic dilated lobes. The proportion between galaxy and lobes, like an ant in the center of a football stadium whose bleachers extend to the horizon and beyond. Actually, the lobes are about 300 times larger than the host galaxy's stellar disk. A completely counterintuitive, always surreal disproportion that defies every expectation based on earthly experience. Imagine holding a penny in your fingers. Now imagine that something emanating from this penny extends 3 meters around in all directions proportionally. That's approximately the proportion we're dealing with. Something so small, generating a structure so colossally larger, defying all expectations based on everyday terrestrial experience. It's like finding that a grain of sand has somehow built the Empire State Building. The human brain processes sizes using hierarchical categories: small, medium, large, very large, enormous, colossal, each category with vaguely defined limits that evolve to handle objects in our immediate environment. When an object transcends all mentally predefined existing categories, the brain simply gives up. It classifies everything above a certain threshold as generically very large and moves on. This isn't a cognitive failure or a personal limitation. It's efficient, evolutionary, adaptive economy functionally necessary for ancestral survival in the primitive, ancient, historical African savanna. Our ancestors needed to distinguish between a 1-meter snake and a 2-meter snake because that difference could mean life or death. They didn't need to distinguish between 16 million and 23 million light-years because such distinctions provided no survival advantage. Natural selection didn't favor genes for intuitive cosmic comprehension. It favored genes for avoiding predators, finding food, reproducing efficiently, raising offspring successfully. The ability to instantly judge whether a charging mammoth was 50 or 100 meters away could mean the difference between survival and extinction. The ability to contemplate galactic jets provided no reproductive advantage whatsoever. Paradoxically, this very limitation gave us mathematics, an abstract tool that transcends biological intuition, allowing us to navigate the universe conceptually, computationally, theoretically, formally, logically. We evolved brains too small for the cosmos, then invented symbolic languages capable of describing infinities. We transcended our biological constraints through cultural evolution. We can calculate that Alcyoneus spans 16 million light-years. We cannot feel this distance viscerally, the way we feel 10 meters when walking across a room. The number exists in our mathematical consciousness, processed by our frontal cortex, but not in our embodied spatial experience. It's knowledge without feeling, information without visceral comprehension. Computer simulations help bridge this gap between calculation and experience. We can fly through Alcyoneus virtually, zoom from the central galaxy to the radiolobes in seconds of screen time. But the experience remains fundamentally abstract, dissociated from tangible physical reality, where watching pixels represent distances that dwarf our solar system. The map is not the territory, and the simulation is not the cosmos. Even experienced professional astronomers who work with these scales daily admit they work with numbers and graphs, not with true intuitive understanding of the scales actually proportionally involved. They manipulate equations that describe cosmic giants, but their gut feelings about distance remain calibrated for terrestrial scales. A lifetime of studying the universe doesn't fundamentally rewire our savanna-adapted spatial intuition. Martin Oé, discoverer of Alcyoneus, said he didn't immediately perceive the magnitude of his discovery when he first saw the data. His brain, trained and experienced as it was, also initially underestimated the scale naturally and intuitively. Even the expert who first detected these cosmic jets didn't immediately grasp what he was seeing. The discovery was intellectual, mathematical, computational, not visceral or intuitive. This humility is crucial for honest scientific inquiry. Recognizing cognitive limits isn't weakness. It's the self-awareness necessary to seek knowledge honestly, humbly, truly. Admitting that our brains can't intuitively grasp cosmic scales doesn't diminish the achievement of detecting and measuring them. It makes the achievement more remarkable, not less. It celebrates human ingenuity in transcending biological limitations. But biological limitations don't prevent us from appreciating the cosmic sublime. We can admire without fully comprehending, marvel at the incomprehensible, abstract transcendent. Alcyoneus continuously releases energy through its jets, power equivalent to trillions of suns blazing simultaneously, perpetually, without ever ceasing. To be specific, about 10 to the 39th power watts, a number with 39 zeros after the first digit. If we tried to write this number in full, we would need a line approximately 12 centimeters long just for the zeros alone. Think about what this means for a moment. This energy is sufficient to heat the intergalactic medium for millions of light years in all directions, radiating spherically, always expanding outward, like an invisible furnace warming the cosmic void. It's not just bright in the conventional sense. It's literally redefining the temperature and composition of space itself across distances that dwarf entire galactic clusters. Porphyrion is even more powerful. Its combined jets produce energy equivalent to 13 trillion times the brightness of our sun, continuously, always, without pause. Here's a terrestrial comparison that might help you process this scale. All energy used by human civilization in an entire year equals 0.5 seconds of Porphyrion's constant production. Half a second, less time than it takes to blink. The entire history of human civilization, from the first Sumerian cities 6,000 years ago, through every empire, every technological revolution, every war, to today's global energy consumption, represents about 3 hours of Porphyrion's energy output. Every war fought, every city built, every light bulb ever turned on, every computer ever powered, every car ever driven, every factory ever operated. All of human energy consumption across 6 millennia equals what Porphyrion produces during a long lunch break. These numbers begin to lose all anchorage with reality. Trillions of suns, 39 zeros, everything becomes pure distilled formal mathematical abstraction. Our brains, designed over millions of years to process the energy output of campfires and the kinetic force of thrown spears, encounter numbers that slide off consciousness like water off glass. The digits become meaningless symbols rather than quantities we can relate to any earthly experience. Let's try another perspective that might ground these incomprehensible scales. What volume of space does Alcyonius actually occupy three-dimensionally, physically, totally, completely? Assuming the radio lobes are approximately spherical, each has a radius of about 8 million light-years from the original galactic center. The volume of a sphere equals 4/3 of pi times radius, cubed, basic fundamental geometric calculation, always mathematically constant across the universe. Each lobe occupies approximately 2.14 x 10 to the 21st power cubic light-years, a number with 21 sequential digital zeros marching across the page. To compare this with something we might recognize, the entire Milky Way, our home galaxy with its hundreds of billions of stars, occupies about 7. 9x10 to the 15th power cubic light-years proportionally and spatially. Alcyonius is approximately 270,000 times more voluminous than the Milky Way, like comparing an Olympic swimming pool to a tiny water droplet. But here's the paradox that should make you pause and consider the strange nature of cosmic structures. This enormous volume is almost completely empty. The average density is billions of times lower than the best vacuum artificially created in terrestrial laboratories. If we somehow compressed all matter from Alcyonius's lobes into a single mass, we would have perhaps a few 100 million solar masses of dispersed, rarefied plasma. It's like inflating a soap bubble to the size of a cathedral, stretching infinitesimally thin material over an enormous volume, making it almost transparent, almost imperceptible, almost ghostly, and always translucent. We're looking at something that occupies more space than 250,000 galaxies, but contains less actual matter than most single stars. This plasma travels at relativistic velocities that bend our understanding of physics between 50% and 99% of light speed, depending on distance from the central emitting black hole. At 90% of light speed, particles experience temporal dilation. Time passes 2.3 times slower for them than for us external observers. At 95% light speed, time slows by a factor of 3. At 99% light speed, time crawls by 7 times slower. For particles traveling at 99.9% of light speed, time practically stops relative to our reference frame. 1 terrestrial year equals only 16 days subjectively experienced by them. They exist in a temporal bubble where the universe around them appears frozen in slow motion while they traverse cosmic distances at nearly light speed. This means that particles in the jets experience the 16 million light-year journey as much shorter subjectively and temporally. For us external observers, The jets took approximately 50 million years to grow to their current size. For the particles themselves, racing through space at near light speed, it was much less subjective personal time. They're riding the cosmic express train, experiencing the universe in slow motion while covering impossible distances. Special relativity introduces another layer of complexity that fragments our intuitive understanding. Time is not absolute. Space is not absolute. Everything depends on relative observational motion. The faster you move through space, the slower you move through time. At extreme speeds approaching light, time nearly stops. Distances contract along your direction of motion, and your mass approaches infinity. Physics becomes poetry at these scales. The light we see from Alcyonius took 3 billion years to arrive at our telescopes. We see the galaxy as it was when Earth was only 1.5 billion years old, a very different world. At that primitive terrestrial epoch, only single-celled organisms existed in the primordial oceans. Complex multicellular life had not yet emerged. There were no plants, no animals, no continents as we know them. Dinosaurs were still 2.5 billion years in the future. Humans were 3 billion years away from existing, so we observe Alcyonius simultaneously in its distant past and our present moment. Astronomical observation is always partial, indirect, always retrospective, temporal travel. We cannot see the universe as it exists now, only as it was when light began its journey toward us across the cosmic void. Information cannot travel faster than light, universally and limitedly according to the laws of physics. If Alcyonius somehow disappeared today, vanished completely from existence, we wouldn't know for 3 billion years. The light showing us its current state would continue arriving for 3 billion years after its hypothetical destruction. This fragments our understanding fundamentally. We see the universe not as it is, but as it was. Temporal layers superimposed confusingly, intricately, complexly, always simultaneously creating a palimpsest of cosmic history. Every direction we look is a different moment in cosmic history. The farther we peer into space, the further back in time we travel. The edge of the observable universe shows the cosmos as it was only 380,000 years after the Big Bang, when the universe first became transparent to light, when electrons and protons first combined to form neutral hydrogen atoms, when the cosmic microwave background radiation we still detect today began its 8 billion year journey to our sensitive instruments. The observable universe has a radius of 46.5 billion light-years, larger than the universe's age of 13.8 billion years, because space itself expanded while light was traveling toward us perpetually. The fabric of space-time stretched during the photon's journey, carrying distant galaxies beyond their apparent distance when the light first departed. The universe is not only vast, but actively growing vaster every moment through cosmic expansion. If we scaled the entire observable universe to Earth's dimensions, the Milky Way would shrink below individual, isolated subatomic particles, invisible microscopically even to our most powerful instruments. Alcyonius, even at this drastically compressed scale, would be only a few atoms. Still invisible to the naked eye, still proportionally incomprehensible visually, still beyond direct human perception. In the observable universe, astronomers estimate approximately 2 trillion galaxies based on deep field observations. If we counted one galaxy per second without stopping, it would take 63,000 years just to enumerate all existing ones, longer than recorded human history. Each galaxy contains billions or trillions of stars. The total number of stars in the observable universe is approximately 10 to the 24th power, a 1 followed by 24 zeros. This number is larger than all grains of sand on all beaches on Earth, about 100,000 times larger proportionally and comparatively, and each star may have planets orbiting it. Recent discoveries suggest planetary systems are common, perhaps universal. The potential number of planets in the universe is astronomically larger than the number of observable, countable, detectable stars. There may be more worlds than there are atoms in your entire body. Faced with this overwhelming immensity, even Alcyonius seems small, just one structure among trillions, just one example among infinite universal possibilities. This perspective is vertiginous and humbling. We are cosmically insignificant in terms of size and duration, but also intrinsically part of this vastness, connected through shared atoms and ancestral evolutionary history spanning billions of years. The carbon in our bodies was forged in the cores of dying stars billions of years ago. We are literally made of recycled stardust from ancient explosive supernovas that scattered heavy elements across space. The calcium in our bones, the iron in our blood, the oxygen we breathe with every breath, all created in stellar furnaces that died long before our solar system formed. We are not separate from the cosmos. We are the cosmos becoming aware of itself through conscious observation. Every atom in your body has already traveled billions of light years through the cosmos before finding itself here, now, temporarily and briefly forming you. Alcyonius is not merely large. It's a challenging scientific enigma that fundamentally questions our understanding of galactic structure growth. The host galaxy is surprisingly normal. Median stellar mass, modest black hole, extremely low star formation rate of only 0.016 solar masses per year. It's the galactic equivalent of a quiet suburban neighborhood. Why then did its jets grow so disproportionately? We would expect giant jets from exceptionally massive galaxies or colossal, extreme supermassive black holes. Previous theories suggested that only more massive galaxies or larger black holes would produce the most extensive, observable, detectable jets. Always proportionally, there should be a correlation between the size of the engine and the scale of its output. Alcyonius proves this correlation isn't absolute. Even modest systems can generate colossal structures under specific favorable environmental conditions. It's like discovering that a small motorcycle engine has somehow powered a freight train across a continent. The relationship between cause and effect breaks down at cosmic scales. The key may lie in the environment itself. Alcyonius resides in a low-density region, a tenuous filament of the rarefied intergalactic cosmic web. With fewer obstacles, jets encounter less resistance. Plasma travels farther before decelerating and forming visible, detectable terminal lobes. It's like the difference between a river flowing through open plains versus one constrained by narrow canyon walls. Think of it like water from a garden hose. If there are no obstacles, the jet travels far. If there's a nearby wall, it ricochets and spreads prematurely, rapidly, immediately. The environment shapes the outcome as much as the initial force. Alcyonius found itself in cosmic open country with room to grow. The density of the intergalactic medium in filaments is approximately 10 to the -5th power atoms per cubic centimeter, absurdly rarefied compared to anything we experience. To put this in perspective, the best laboratory vacuum on Earth still contains millions of times more particles than the typical average common observed intergalactic medium. Porphyrion, even more temporally distant, existed when the universe had half its current age. Densities were 8 times higher, then proportionally. Yet it still grew to 23 million light years. This suggests that other factors beyond environmental density also significantly influence jet growth. There's more to this cosmic recipe than just empty space. The orientation of the black hole may matter crucially. If it remains stable for billions of years, jets maintain consistent direction, avoiding dispersive destabilizing curvature. Porphyrion is remarkably straight. It deviates less than 5 degrees along its entire 23 million light-year extent, a consistency that's always surprising given the dynamic nature of cosmic environments. Maintaining direction for 23 million light-years in a dynamic environment is like firing an arrow that hits a target 1,000 kilometers away without deviating. The precision required defies intuition. Something must be guiding these jets along nearly perfect straight lines across cosmic distances. Intergalactic magnetic fields may stabilize the jets. Field lines act like invisible rails, guiding plasma in narrow collimated rectilinear trajectories. These magnetic highways channel the plasma like train tracks channel locomotives. But here's the beautiful cosmic irony. These jets may be responsible for creating the very magnetic fields that stabilize them, a self-organizing, self-sustaining cosmic feedback loop. The plasma in the jets carries magnetic fields with it. As it spreads outward, it literally paints the intergalactic medium with persistent, enduring diffuse magnetism. Radio polarization observations confirm this. Cosmic voids contain weak magnetic fields, possibly originated from jets like ancestral Alcyoneus and Porphyrion. This means that supermassive black holes may have magnetized the entire universe over billions of evolutionary years, transformatively and gradually. The magnetic field of Earth, which protects life from cosmic radiation, may have remote connections to jets from ancient, primordial distant galaxies. Everything is connected across scales we can barely comprehend. Terrestrial magnetism links to the Sun, which links to the Milky Way, which may link to universal intergalactic cosmic fields. This cosmic magnetic network may have influenced galaxy formation in the primitive universe, affecting gravitational collapse of molecular gas clouds. The structure of the universe may bear the magnetic fingerprints of ancient galactic jets. These jets don't just destroy, they also fertilize space itself. They inject heavy metals into the intergalactic medium. Elements forged in stars of the host galaxy are scattered across millions of distant light-years. Heavy metals here means all elements heavier than helium, carbon, oxygen, iron, gold, all created in ancient stellar nuclear furnaces. Without this metallic dispersal, young galaxies would have fewer heavy elements to form rocky planets like our solid, compact, dense Earth. The jets are cosmic gardeners, enriching the intergalactic medium with ingredients necessary for planets and eventual potential future possible life. Every carbon atom in your body may have traveled millions of light-years before reaching Earth. Alcyoneus has been active for approximately 50 million years, sufficient time for jets to grow to their current observed, detected, measurable, estimated size. But the black hole may have had previous active phases. Jets could be intermittent, switching on and off as feeding varies temporally and cyclically. What we see may be just the latest episode in a billion-year saga. Observing jets is like seeing a frozen photograph. We don't see complete dynamics, only a snapshot of processes unfolding over cosmic eras. The jets may be decelerating now. Without new energy injections, they will eventually fade over millions of future years, progressively and gradually. Or they may accelerate again if the black hole receives new influxes of matter. The system is dynamic, always changing on immense cosmological temporal scales. Galaxies merge, bringing fresh gas to feed the central black hole. Each feeding episode could trigger new jet activity. The discovery of more than 10,000 giant radio galaxies suggests this phase is common in galactic evolution, not a rare anomalous exception. Perhaps all massive galaxies pass through a giant jet phase at some point. We're seeing Alcyoneus at a specific moment in its long life, like catching a caterpillar in the brief moment it becomes a butterfly. The Milky Way may have had jets in the past. Evidence suggests Sagittarius A was much more active billions of years ago. The Fermi bubbles, gamma-ray structures above and below the galactic disk, may be relics of ancient, extinct, dormant, currently inactive jets. Ghosts of our galaxy's more violent youth. If the Milky Way had jets, they were minuscule compared to Alcyoneus, perhaps only tens of thousands of light years, not millions extensively. This shows cosmic diversity. Not all galaxies follow the same evolutionary pattern. Variability is the norm, not universal standardized uniformity. Alcyoneus represents an extreme of this distribution, a statistical outlier that reveals maximum possibilities nature is capable of under ideal, perfect rare conditions, like studying the tallest mountain to understand how high peaks can grow, or the deepest ocean trench to understand how far down we can go. Studying extremes illuminates general rules. Understanding Alcyoneus helps us better understand all radio galaxies and the processes that govern them universally and fundamentally. Confronted by Alcyoneus, inevitable questions arise. What is our place in a universe so incomprehensibly vast and ancient, so filled with structures that dwarf our entire galactic neighborhood? Earth is a medium-sized rocky planet orbiting an average star in the suburbs of a common galaxy within a typical filament of the cosmic web. There is nothing special about our cosmic location. We are completely ordinary in astronomical, observational, detectable, always immeasurable technical terms. The Copernican principle states this clearly and unequivocally. We occupy no privileged position in the universe, neither spatially nor temporally, nor in any other measurable physical dimension. This realization is profoundly humbling when we truly absorb its implications. All human greatness, all recorded history, all art, all war, all love, all suffering happened on this insignificant point in the infinite, expansive cosmos. Every empire that ever rose and fell, every love story ever told, every scientific breakthrough ever achieved, all occurred on a mote of dust suspended in cosmic vastness. Carl Sagan captured this perspective perfectly when he called Earth a pale blue dot. In Voyager 1's famous 1990 photograph taken from the edge of the solar system, Earth appears as a tiny pixel suspended in a sunbeam. On it, Sagan wrote, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives, the aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization. Every human construction we consider monumental, from the Great Wall of China to the Egyptian pyramids, from Machu Picchu to the International Space Station, from the Parthenon to the Golden Gate Bridge, is invisible from that distance, completely erased by the surrounding vastness of space. The cosmic perspective exposes the ultimate futility of many territorial conflicts. Wars fought over terrestrial territories seem absurd when the entire territory is a microscopically atomic invisible point, lost in infinite darkness. But there's a profound and beautiful paradox here. Smallness doesn't imply insignificance. Scale doesn't determine value. Importance is not a function of proportional, measurable physical size. A poem written on Earth carries no less meaning because Earth is small compared to Jupiter. A mother's love for her child is not diminished because both exist on a cosmic speck. The first words of a child learning to speak are not less miraculous because they occur in an ordinary solar system. We are products of 13.8 billion years of cosmic evolution, from the Big Bang's first moments through stellar nucleosynthesis to planetary formation to biological evolution to consciousness. An improbable series of events and coincidences that culminated here in minds capable of contemplating their own origins and questioning their place in the vast scheme of existence. The atoms in our bodies formed in stars billions of years ago, in nuclear furnaces burning at temperatures of millions of degrees. We are literally stellar dust reorganized into complex conscious thinking patterns. The carbon that forms our DNA, the oxygen we breathe, the calcium in our bones, the iron in our blood, all forged in stellar cores or scattered by violent energetic supernova explosions across the cosmos. it took billions of years for the universe to produce sufficient heavy elements to make life possible. The first generation of stars contained only hydrogen and helium, created in the Big Bang. No carbon, no oxygen, no silicon, no iron. Nothing heavier than lithium. Carbon-based life as we know it only became possible after several generations of stars lived their entire life cycles and died, progressively enriching the cosmos with heavier elements through their death throes. So our very existence depended fundamentally on the death of ancestral stars. We are heirs to cosmic explosions, children of nuclear furnaces extinct for eons before our solar system even formed. We carry within our bodies the ashes of stellar giants that once illuminated regions of space now dark and cold. We are the universe, becoming aware of itself through the gradual evolution of matter into increasingly complex patterns culminating in mind. Earth formed 4.54 billion years ago from a protoplanetary disk of gas and dust around the young sun, a process that has been repeated trillions of times throughout the universe, creating countless worlds orbiting distant stars. Life emerged surprisingly quickly by geological standards. Evidence of single-celled organisms exists from 3.8 billion years ago, only 700 million years after planetary formation and the end of the late heavy bombardment. But it took an additional 3.5 billion years for a complex multicellular life to evolve. The vast majority of Earth's biological history was microbial, unicellular, simple, basic. For most of Earth's existence, the most complex organisms were bacterial mats and algae. The Cambrian explosion of complex life occurred only 540 million years ago, a recent event in planetary terms. Modern humans have existed for only about 300,000 years. If Earth's entire 454 billion year history were compressed into a single calendar year, humans would appear at 11:56 p.m. on December 31st. Civilization began a mere 10,000 years ago with the agricultural revolution, representing the last 15 seconds of that hypothetical, compressed temporal year, a minuscule fraction of available time. All recorded history, all science, all art, all human technology developed in those metaphorical 15 seconds. An explosion of complexity and knowledge in what amounts to a cosmic blink of an eye. Yet, in that brief moment, we developed consciousness sophisticated enough to ponder our origins, language complex enough to describe abstract mathematics, and telescopes powerful enough to detect Alcyonius 3 billion light-years distant. We represent the universe, developing the capacity to reflect on itself introspectively, philosophically, consciously, systematically. Through us, the cosmos examines its own structure, contemplates its own history, and seeks to understand its own destiny. We are matter arranged in such a way that it can think about matter. Consciousness evolved to the point where it can study consciousness. This capacity appears to be extraordinarily rare in the observable universe. Among the estimated 2 trillion galaxies containing perhaps 10 and 24 stars and an even larger number of planets, we know of no other world with definitively verified, confirmed, intelligent life. The profound silence of the cosmos raises disturbing questions about the nature and fate of consciousness. The Fermi paradox poses the haunting question that keeps many scientists awake at night. If the universe is so vast, so old, so filled with potentially habitable worlds, where is everybody? Why don't we detect other technically advanced communicative civilizations? Why do we seem to be alone in a cosmos that should, statistically, be teeming with intelligence? Perhaps intelligent life is extremely rare, requiring such an unlikely sequence of events and circumstances that it occurs only once in billions of star systems. Perhaps we are among the first civilizations to emerge, or among the last. Or perhaps we are unique in a vast region of the silent, empty intergalactic cosmos. The thought is both terrifying and awe-inspiring. Or perhaps advanced civilizations inevitably self-destruct rapidly. Intelligent life might be common throughout the galaxy, but short-lived, unstable, paradoxically evolutionarily self-destructive. The universe might be littered with the ruins of civilizations that discovered nuclear weapons, or genetic engineering, or artificial intelligence, or nanotechnology before discovering the wisdom to use these powers responsibly. Or perhaps we are simply too young and primitive to recognize the signs. Ancient civilizations, millions of years ahead of us, might use forms of communication we don't recognize, technologies invisible to our limited instruments. They might communicate through gravitational waves, or quantum entanglement, or methods we haven't even imagined. They might be all around us, as invisible to us as radio waves were to our ancestors just centuries ago. Regardless of which answer proves correct, our responsibility remains constant and clear. Preserve this precious spark of consciousness, this rare capacity to comprehend the surrounding universe and our place within it. Alcyoneus reminds us that we are cosmically small, but also infinitely precious. We manage to detect it across 3 billion light-years, measure its impossible scale, and understand its physical nature mathematically, despite the severe cognitive limitations imposed by our evolutionary heritage. The human capacity to transcend biological limitations through mathematics, technology, and collaborative inquiry is extraordinary, almost miraculous, from an evolutionary perspective. A 4-kilogram brain, originally evolved to survive on the African savanna, now comprehends structures spanning 16 million light-years through sophisticated abstract calculations and technological extensions of our senses. This represents a triumph of curiosity over limitation, imagination over instinct, reason over immediate restricted sensory perception, culture over biology. We have become more than our evolutionary programming intended. We have transcended our origins through the accumulated wisdom and tools of civilization. But this triumph doesn't eliminate the need for humility. If anything, it demands greater humility. The more we discover, the more we perceive the vastness of what remains unknown. The persistent residual depth of our ignorance becomes more apparent with each answer. Knowledge is an island of understanding expanding in an infinite ocean of ignorance. The larger our island of knowledge grows, the longer its coastline of contact with the mysterious, unexplored unknown. And in this process of perpetual search and discovery, we find significance, not in cosmic grandeur or physical scale, but in the distinctly human capacity to admire, question, and seek truth tirelessly and relentlessly. Let's retrace our entire journey. We began with Earth 40,000 kilometers in circumference, familiar, tangible, directly measurable, with simple, basic terrestrial instruments. Something we could walk across, something we could hold in our minds as a complete object, our home, our reference point, our starting place for understanding everything beyond. We expanded to the solar system, 8 planets orbiting the sun in a gravitational dance, extending billions of kilometers through spatial void. We discovered that even our cosmic neighborhood, the realm we thought we knew, stretches beyond easy comprehension. Mars, at its farthest, is 400 million kilometers away, distances requiring months of travel even for our fastest spacecraft. We leaped to nearby stars, Proxima Centauri at 424 light-years, Sirius at 8.6, Betelgeuse at 550, each jump multiplying distance dramatically and exponentially. We learned that the space between stars is almost incomprehensibly empty, that our sun is just one ordinary star among hundreds of billions, that the stellar neighborhood we can see with naked eyes represents only the tiniest fraction of our galactic surroundings. We embraced the Milky Way, 100,000 light-years in diameter, containing 200 to 400 billion stars, a majestic spiral slowly rotating in the intergalactic cosmic void. We discovered we live in a galaxy so vast that light takes 100,000 years to cross it, so populous that counting its stars one per second would require thousands of years, so ancient that it has completed fewer than 60 rotations since its formation. We encountered galactic neighbors, Andromeda at 2.5 million light-years, the local group, the Virgo cluster, the Laniakea supercluster, structures growing ever larger. We realized our galaxy is just one among thousands in our local neighborhood, that galactic clusters span hundreds of millions of light-years, that we belong to gravitationally bound structures containing hundreds of thousands of galaxies. We comprehended the cosmic web, interwoven filaments of galaxies, immense voids, the fundamental architecture of the universe, revealed through meticulous, detailed, systematic astronomical surveys. We learned that matter organizes on the largest scales into a foam-like structure with galaxies strung along invisible filaments of dark matter like pearls on cosmic strings, separated by voids so empty they contain almost nothing. We discovered giant galaxies, IC 1101 spanning 6 million light-years, Hercules A with jets extending 1.5 million light-years, structures always challenging previous expectations. We found that our assumptions about maximum galactic sizes were conservative, that the universe contains galaxies hundreds of times larger than our own, that individual objects can compete in scale with the distances between galactic clusters. Finally, we confronted Alcyonius, 16 million light-years in extent, 240 billion solar masses, jets continuously releasing the energy of trillions of suns. We encountered something so large that our entire galaxy could be lined up 160 times across its structure, something so energetic it outshines entire galactic clusters, something so ancient its light carries information from when Earth was a fundamentally different world, and Porphyrion even larger, 23 million light-years across, existing when the universe had half its current age, traversing significant portions of the primordial cosmic web. We discovered that the early universe contained structures even more colossal than those we see today, that cosmic architecture has been shaped by objects operating on scales we're only beginning to comprehend. Each stage of our journey amplified scale by factors of thousands, from meters to kilometers to light-years to millions of light-years, an exponential progression that rapidly outpaced our intuitive understanding. We climbed a ladder where each rung represented not just the next level, but an entirely different category of existence, and each stage revealed that our previous understanding was merely prologue. There's always something larger, always the next layer of reality, awaiting future exploration. Every time we thought we had grasped the maximum scale of cosmic structures, new discoveries forced us to revise our estimates upward by orders of magnitude. We attempted analogies to make these scales comprehensible. Football fields, grains of sand, Olympic pools, all inevitably inadequate to capture true proportional magnitude. Every comparison we created eventually collapsed under the weight of the numbers we were trying to convey. Our terrestrial references proved insufficient for cosmic realities. We compressed time to understand space, representing light-years as seconds, 16 million light-years as 6 months. An attempt to make spatial what is fundamentally temporal. But even these temporal analogies failed to bridge the gap between calculation and comprehension. 6 months feels manageable until you remember it represents distances light itself requires millions of years to traverse. We scaled proportions desperately. Basketball Earth, golf ball Earth, always finding that reduction merely displaced the problem without solving the fundamental intrinsic cognitive limitation. Making Earth smaller didn't make Alcyonius more comprehensible. It simply moved the incomprehensibility to a different scale. We confronted pure numbers, 10 to the 39th power watts, 2 trillion galaxies, 10 to the 24th power stars, mathematical abstractions distilled and formalized beyond everyday experience. We learned that at cosmic scales, numbers become more like poetry than mathematics, symbols representing quantities so large they exist only in the realm of pure thought. We recognize that numbers are not understanding. We can calculate without visualizing, quantify without truly intuiting. The distinction between mathematical knowledge and visceral comprehension became clear. We can manipulate cosmic equations without feeling cosmic scales. The map is not the territory, and the calculation is not the experience. This limitation is not a defect in human cognition. It's an evolutionary characteristic, cognitive economy, that allows our brains to function efficiently in everyday terrestrial environments. We evolved to distinguish between threatening and non-threatening objects within a few hundred meters, not to intuitively grasp intergalactic distances. Our neural architecture was shaped by survival needs, not astronomical requirements. But we transcended this limitation through tools: mathematics, telescopes, computer simulations, artificial extensions of our original evolutionarily adapted biological cognition. We created technologies that amplify our senses across cosmic distances, mathematical languages that describe what we cannot directly perceive, collaborative methods that combine thousands of minds across generations. Alcyoneus teaches us humility, not just about physical size, but about the limits of direct, intuitive, immediate sensory human knowledge. It reminds us that reality extends far beyond the boundaries of personal experience, that the universe operates according to principles and scales that dwarf our everyday concerns. But Alcyoneus also teaches hope. Despite our cognitive limitations, we detected this structure across 3 billion light-years, understood the physics of relativistic jets, unraveled cosmic mysteries using instruments and mathematics. We proved that biological constraints need not prevent discovery, that cultural evolution can transcend evolutionary programming. We are simultaneously insignificant and extraordinary, conscious grains of dust in a vast cosmos, but grains capable of comprehending the entire cosmos conceptually and mathematically. Our physical scale is minuscule, but our intellectual reach spans the observable universe. We are matter arranged in such a way that it can contemplate the arrangement of all matter. Our cosmic location is utterly ordinary, but our existence represents something miraculous. Trillions of improbable events aligned perfectly to allow consciousness to emerge gradually and evolutionarily: the formation of heavy elements in stellar cores, the precise orbital characteristics that keep Earth habitable, the survival of life through multiple mass extinction events. Each step in our existence required winning cosmic lottery after cosmic lottery. We exist because ancestral stars died billions of years ago, scattering heavy elements through space, because Earth formed in the habitable zone around a stable star, because life persisted through devastating catastrophic mass extinctions, because evolution stumbled upon the neural arrangements that generate consciousness. The chain of causation leading to minds capable of contemplating Alcyoneus stretches back to the first moments after the Big Bang. Each of us represents the culmination of 3.8 billion years of uninterrupted biological evolution, a genealogical chain that never broke from the first primordial cell to the present moment. Every ancestor in that impossible lineage survived long enough to reproduce, passing genetic information forward through geological ages, through asteroid impacts and ice ages, and volcanic catastrophes. And now, as the most recent links in that ancient chain, we contemplate Alcyoneus, a galaxy that existed when the ancestors of mammals were tiny and insignificant, still primitive compared to the complex forms that would eventually evolve. The light we see from Alcyoneus carries information from a universe when multicellular life was just beginning to experiment with complex forms. The light we observe from Alcyoneus represents an ancient message, photons, that traveled 3 billion years to reach our eyes here and now. These photons existed before Earth had abundant atmospheric oxygen, before complex multicellular life evolved in ancient planetary primordial oceans. They carry information from a universe fundamentally different from the one we inhabit. So observing Alcyoneus means looking simultaneously into deep space and deep time. Astronomy functions as cosmic archaeology, excavating the history of the observable universe layer by layer. Each distant galaxy represents not just another place, but another time. The farther we look, the further into the past we peer. Each astronomical discovery reveals not just where we are, but where we came from. Cosmic history is our history. Stellar origins are our ancestral origins. The calcium in our bones was forged in stellar cores. The oxygen we breathe was created in massive stellar explosions. We are not separate from cosmic evolution. We are cosmic evolution becoming aware of itself. Alcyoneus poses no threat to us. It exists billions of light years away. Its jets will never reach the Milky Way. No danger awaits us from this remote source. But it serves as a reminder that the universe operates on scales that completely transcend trivial, everyday, immediate local, temporal human concerns, territorial wars, ideological conflicts, resource disputes. Everything seems absurd when contextualized against structures spanning 16 million light-years across the entire cosmos. The cosmic perspective doesn't solve terrestrial problems directly, but it offers a different framework, reminding us of our shared fragility as a unique, isolated planetary species. All humans, regardless of nationality, religion, or ideology, share the same tiny planet orbiting a common star in an ordinary, typical universal galaxy. Our differences, which seem so significant from inside human society, appear almost invisible from cosmic perspective. Terrestrial divisions seem artificial when confronted with fundamental cosmic unity. We are all temporarily organized stardust, conscious thinking, living self-aware patterns that emerged from the same evolutionary process on the same small world. Perhaps Alcyoneus can inspire cooperation. If we could unite to build LOFAR, a European network of telescopes, we might unite to address other existential challenges. Science represents collaborative international enterprise. The discovery of Alcyoneus involved researchers from multiple nations working together harmoniously, cooperatively, always productively. This model of peaceful transnational cooperation could extend beyond astronomy. Climate change, pandemics, poverty, all require coordinated collective global effort. We shouldn't romanticize this cooperation. Science also involves politics, disputes, competition. It's not a perfect idealized utopia, just better than currently available alternatives. But the capacity of our young species to detect Alcyoneus suggests tremendous potential. If we survive our self-imposed limitations, a future of cosmic exploration awaits patiently and eternally. We return to the original fundamental question: why is Alcyoneus too large for the human brain to truly, intuitively, viscerally comprehend? The simple answer is that evolution didn't equip us for this. Our brains are optimized for human terrestrial scale, not cosmic intergalactic astronomical scale. We evolved to navigate forests and savannas, not galactic jets spanning millions of light years. But the complete answer is richer and more nuanced. Cognitive limitation doesn't prevent us from knowing, only from intuiting, a crucial fundamental distinction that's always significant. Knowledge doesn't require intuition. We can know that 16 million light years represents a real distance without feeling that distance viscerally, corporally, physically. The intellectual understanding operates independently of embodied comprehension. Mathematics serves as a bridge between limitation and comprehension, a universal language that allows us to navigate scales completely inaccessible to direct sensory perception. Through equations and calculations, we can work with cosmic distances our minds cannot visualize. Numbers become our ambassadors to realms beyond biological experience. Telescopes function as extensions of our eyes. They see invisible radiation, detect objects beyond the visual horizon, amplify our natural evolutionary sensory capabilities. Radio telescopes like LOFAR capture emissions our eyes cannot perceive, revealing structures hidden in frequencies outside human perception. They are technological organs that expand our sensory boundaries. Computers represent extensions of our brains. They calculate faster than any human mind, store more information than any individual memory, simulate virtual universes impossible to contemplate mentally. Through computational modeling, we can fly through digital representations of cosmic structures, experiencing scales that would otherwise remain forever abstract. We are fundamentally a technological species. We overcome biological limitations through tools, an ability that distinguishes us from other known forms of terrestrial life. Our capacity to create instruments that transcend our natural capabilities may be our most defining characteristic. We are biological beings who have learned to become more than biology intended. ʻOumuamua becomes accessible through these technological extensions. LOFAR images, mathematical calculations, computer simulations make this galaxy knowable, if not always clearly intuitive. We cannot feel its scale in our bones, but we can map its structure, measure its energy output, understand its physical processes. Knowledge mediated by technology is still genuine knowledge. This technologically mediated accessibility represents a triumph, not of nature, but of culture. The accumulation of knowledge transmitted across successive human generations throughout history, no individual could discover Alcyonius alone. It requires centuries of scientific development, thousands of minds contributing across progressive historical time. Every observation builds on previous observations. Every instrument improves on earlier designs. Isaac Newton famously said, "If I have seen further, it is by standing on the shoulders of giants," acknowledging his debt to historical scientific predecessors. Today, we see Alcyonius, while standing on the shoulders of generations of astronomers, physicists, engineers, mathematicians, all contributing piece by piece, patiently and meticulously, always progressively. The discovery emerges from collective efforts spanning centuries. Science operates as a cumulative enterprise. Each discovery builds on previous ones. Knowledge grows incrementally over centuries of coordinated collective human effort. But this growth is not linear. There are revolutions, broken paradigms, ancient ideas discarded when evidence contradicts firmly entrenched expectations. Progress comes through both steady accumulation and sudden leaps. Alcyonius challenged existing paradigms. We expected jets wouldn't extend far beyond their host galaxies, but they traverse significant fractions of the observable universe, always unexpectedly. Each broken paradigm expands the frontier of the knowable. Before LOFAR's sensitivity, Alcyonius was invisible, literally beyond detection, not just beyond knowledge. Future technology will reveal even larger structures. Perhaps jets spanning 50 or 100 million light-years, perhaps entirely new categories of unimaginable cosmic objects. The limits of current knowledge are not limits of possible knowledge. There's always more to discover, always the next frontier awaiting future exploration. Each answer generates new questions. Each telescope reveals previously invisible phenomena. This should humble us. Our present knowledge, however vast it seems, is probably minuscule compared to what remains unknown, mysterious, unexplored, but it should also energize us. Each answer generates new questions. Each discovery opens new fields of investigation. Progress continues perpetually. The universe keeps surprising us with scales and phenomena beyond our current imagination. How do we live daily knowing about Alcyonius's immensity? How do we integrate cosmic perspective into everyday terrestrial existence? First, accept that incomprehensibility is not personal failure. It's a universal limitation shared by all biologically evolved human beings. Our cognitive constraints are species-wide, not individual shortcomings. Second, value our capacity to know even without fully intuiting. Celebrate the triumph of reason over biological sensory limitations. We may not feel cosmic distances, but we can measure them, model them, work with them mathematically. This represents an extraordinary transcendence of evolutionary programming through cultural tools. Third, maintain curiosity alive despite intimidating vastness. Remember that every great discovery began with a simple, basic, fundamental, honest question. Curiosity drives discovery more than sophisticated equipment. The willingness to ask, "What is that?" or "How does this work?" opens pathways to cosmic understanding. Fourth, recognize deep personal existential cosmic connection. The atoms in our bodies came from ancestral stars. We share matter with Alcyonius, literally, materially, physically. We are not separate from cosmic structures. We are made from the same elements, forged in the same stellar furnaces, scattered by the same supernovae. The cosmic and personal are intimately connected. Fifth, use cosmic perspective to contextualize terrestrial problems without trivializing them. Balance cosmic humility with immediate human compassion. Understanding our cosmic insignificance doesn't make personal suffering less real or important. It simply provides a broader framework for understanding our place in existence. Sixth, support science and accessible scientific education ensure future generations can continue discovering incomprehensible cosmic wonders. Scientific literacy is not luxury, but necessity. The capacity to understand our cosmic context should be heritage shared by all humanity, not privilege restricted to specialists. Seventh, communicate discoveries broadly and accessibly. Scientific knowledge shouldn't be elite privilege, but shared patrimony of planetary humanity. The wonder of cosmic discovery belongs to everyone who looks up at the night sky. Complex discoveries need translation into language that inspires rather than intimidates. Eighth, preserve Earth carefully. It's the only known place where consciousness can contemplate Alcyonius, precious beyond any monetary or economic measure. Our planet is not just our home, but the universe's only known vantage point for cosmic self-reflection. Every environmental destruction diminishes the cosmos's capacity for self-awareness. Ninth, seek answers without expecting final definitive ones. Science is a journey without final destination, a perpetual process of progressive refinement. Understanding evolves continuously. Today's certainties become tomorrow's approximations. Intellectual humility keeps discovery alive. 10th, admire without needing to dominate or possess. Alcyonius's beauty doesn't diminish because it's inaccessible. Perhaps it increases precisely because it transcends our reach. Some wonders are meant to be contemplated rather than conquered. Distance preserves mystery and maintains reverence. Alcyonius will continue existing indifferently to our understanding. Its jets will shine in radio wavelengths regardless of whether we observe them. The universe doesn't need conscious human witnesses. But we need Alcyonius, not physically, but existentially, as reminders of the vastness surrounding us, anchors of humility in an era of arrogance. Each generation must rediscover cosmic scale personally. Experience doesn't transmit automatically. Each person must confront immensity individually, subjectively, viscerally. Parents can point out the night sky to children. Teachers can explain astronomy to students. But genuine wonder comes only from personal, direct, intimate encounter with cosmic vastness. This encounter transforms irreversibly. Seeing for the first time that something so vast exists changes perspective permanently. It plants seeds of lasting cosmic reverence. Once you truly grasp that radio galaxies spanning millions of light-years actually exist, your relationship with scale never returns to purely terrestrial concerns. Alcyoneus represents a gift to human civilization, a tangible, measurable reminder that the universe is larger, older, more complex than imagination can fully encompass. In times of growing tribalism, resurgent nationalism, and deep ideological divisions, Alcyoneus offers unifying perspective. We all share the same tiny temporal cosmos. So let's look up occasionally, regularly, frequently. The night sky contains 16 million light-years of humility if we have courage to confront them honestly. Alcyoneus is more than a galaxy. It's a mirror reflecting human limits and potential simultaneously, paradoxically, always inseparably. Its 16 million light-years expose the fragility of human perception, evolutionarily adapted only for immediate local terrestrial scales, but they also celebrate the triumph of human minds through mathematics, technology, international cooperation. We unraveled structures beyond naturally possible intuitive comprehension. We live in an extraordinary era. The first human generation capable of detecting, measuring, studying Alcyoneus through sophisticated instruments developed collectively, patiently, progressively. Previous generations looked at the same night sky but saw only stars. They knew nothing of galaxies, much less jets spanning millions of light-years across the infinite cosmos. Our vision has expanded dramatically, from geocentrism to heliocentrism, to galaxies to cosmic web, each step amplifying our horizon exponentially. Future generations will see even farther. Telescopes yet to be built will reveal universes we can barely imagine with present limited technology. But regardless of how far we advance technologically and scientifically, cognitive limitation will persist. There will always be scales beyond natural human biological intuition. And perhaps that's beautiful. Mystery preserved not by ignorance, but by the very architecture of consciousness, ensuring perpetual humility before the cosmos. Because in the end, completely comprehending Alcyoneus is impossible, but admiring it, celebrating it, learning from it, that remains within our immediate present accessible reach. And perhaps that's always sufficient, not understanding everything, but admiring deeply, sincerely, reverently, recognizing mystery without fearing or denying it completely. If you're still awake, it's because the content was really good. So take a moment, leave a like, and subscribe to the channel. It helps a lot. And if you want to keep watching, just click on the video that's appearing right now. I'll see you there.